So at last we are ready to convert bits into signals, the crux of physical layer. So this process goes by the name of modulation. Before we dig in, a few questions first. I know you're tired of looking at this slide, but it is good to recap for reinforcement. So nodes generate data in the form of bits and links carry signals in the form of electromagnetic waves. So we need to convert these bits into signals. So far we have seen the frequency domain representation of signals. So we also found what is the maximum capacity supported on a link, basically the Shannon's theorem. And we also covered what are the goals of modulation. So with this background, we are ready to convert the data in the form of bits into signals. So this process of converting bits into signals, as I mentioned, is called modulation, and there are two approaches to modulation. One is line encoding. This is also called digital baseband modulation. This is used in Ethernet FDDI. FDDI is a standard for fiber optics. And then there is passband modulation. This is predominantly used in wireless, but some wired links also use passband modulation like ADSL. This stands for asymmetric digital subscriber line. So this is the telephone link that you use for communication. Now in this video, I will provide an overview of both these modulation techniques. In another video, we will get into the details of line encoding. Passband modulation, other than this overview, I will not provide any additional information. This is quite complicated. In fact, one could run a course just on passband modulation. But more importantly, this is used in wireless, and that is not the focus of this course. We have already seen an example of line encoding in the form of NRZ encoding. So in NRZ encoding, a 0 is represented by a low voltage level and 1 by a high voltage level. Do you think if I were to represent 0 by a high voltage and 1 by a low voltage level, things will change? Well, it really doesn't matter as long as you have a consistent policy at the receiver. So in line encoding, the bits are converted into high and low signal voltage levels. So here are two other such line encoding. One goes by the name of Manchester, another by the name NRZI. We will see more of this in detail later. Even here, as you can see, you are making transitions from low to high voltage levels. So the signal waveform has these low voltage levels and high voltage levels. So line encoding is used in Ethernet and fiber optics. As you can see, these waveforms are very easy to generate. So this is a big advantage of line encoding. There are, however, certain limitations to using line codes. One is that the bandwidth of these codes, coded signals, is rather large. Whenever there is a transition, this type of transition from low to high, this typically generates high frequency components. So due to these abrupt changes in the signal, the bandwidth of the signals is large, which in turn means that the bandwidth you need to provide also need to be large. Ideally, when you are converting data into signals, within the signals, you don't want abrupt changes. So you don't want abrupt changes. Another problem with line codes is the presence of a DC component. For example, in this NRZ, if there was a continuous sequence of ones, the voltage level stays high for a long duration, and this can introduce a DC component. Typically in transmission media, you don't want a DC component. For example, you can't do AC coupling via transformers if there is a DC component. A more fundamental problem with line codes is that with these codes, it is not possible to move a signal to a designated spectrum band. What do I mean by this? Let me give an example. So ADSL is a telephone line. And if you want to use this telephone line, apart from making phone calls, to also send data via a modem. You may be aware that voice signal occupies a spectrum between 0 to 4 kHz. Now, while someone is talking on the phone, you may want to send and receive data. in which case this data signal cannot overlap with the voice signal, otherwise they are going to interfere with each other. Suppose let's say we have an NRZ signal of 2000 bits per second. So this is going to occupy a spectrum from 0 to 4 kilohertz. Now if I were to use this NRZ line coding, this signal will definitely interfere with the voice signal. I cannot permit that. So what I have to do is I have to move the signal to some other frequency band. In other words, I can say let the signal occupy a band between 100 to 104 kilohertz. Then I am safe because this is not going to interfere with the voice. Now such shifting of a signal is not feasible via this line codes. So the same issue arises in the wireless domain as well. For example, if you take Wi-Fi has been allocated this band for operation. So whatever signals you are going to send have to occupy frequencies that are within this particular band. This is not feasible through line codes. In passband modulation, the data that you wish to send, the information content of it is embedded in the amplitude, frequency or phase of a carrier signal. By the way, it could be combinations of amplitude, frequency and phase as well. And a carrier signal is nothing but a sinusoid, let's say cos 2 pi fct. Now this fc is called the carrier frequency. Now a passband modulated waveform will have a spectrum centered around this carrier frequency. Suppose you want your waveform to occupy frequencies around, let's say 100 kilohertz, like in the previous example. All you need to do is set your FC around this value. Similarly, if you want your signals to be in the 2.4 gigahertz as required in Wi-Fi, you set the carrier frequency to be around 2.4 gigahertz. Now this passband modulation is used extensively in wireless and also in ADSL. Suppose you are given the data 1101 and a carrier signal cos 2 pi fct, and let's say you want to send this information using this carrier, and let's also say you want to make use of the amplitude of this to convey this data. Think carefully, how are you going to go about it? It's not at all difficult. So as I mentioned, a carrier signal has amplitude in which you can embed information, has frequency you can vary to embed information, and also has a phase also you can embed information. So the same is being shown here. So these are the bits that you wish to send. So in this modulation technique called amplitude shift keying, what you do is you vary the amplitude of the carrier in response to the bits. So for example, when you have to send a 0 bit, you set the amplitude equal to 0, and when you want to send the 1 bit, you set the amplitude to some voltage level, say A. So this is amplitude shift keying. Now in binary frequency shift keying, you manipulate the carrier frequency. For example, if you want to send 0, you do fc minus delta. So this is the signal that you send with this particular frequency, and whenever you want to send a 1, you increase the frequency by fc plus delta and send that particular waveform. So this is frequency shift keying modulation. And in binary phase shift keying, you basically change the phase. For example, when you want to send the 0, you just send cos 2 pi fct, but whenever you want to send the 1, you actually add a phase of 180 degrees to it, and that is the signal you're going to see. As you can see, there is a phase change. It should have gone like this, but because of the phase change, the signal has taken a different direction. By the way, these are very primitive passband modulation techniques. These are not very bandwidth efficient. There are a lot more sophisticated passband modulation techniques which we are not going to cover. Here is a spectrum of the 3 modulation techniques we covered: ASK, BPSK and BFSK. These are supposed to be symmetric around FC. If they are not, it's due to my freehand drawing. Now as you can see, the ASK spectrum is very similar to BPSK except for a component at FC. Now this component is arising because the baseband signal has a DC component. Now that DC components translates to a component at FC. And as you can see, the null to null bandwidths of both of this is 2 RP, even this is 2 RP. For BFSK, you have two components, one at F1, which in this case is set to FC plus RB by 2, and another at F2, which is set to FC minus RB by 2. And the null to null bandwidth of this is equal to 3 RB. So to summarize, there are two approaches towards converting bits into signals. Line codes basically convert bits into high or low voltage levels. Unfortunately, these are not very efficient. But in wires, efficiency is not a very big concern. We will cover a few popular line coding techniques as used in Ethernet. Passband modulation helps shift signals to a desired frequency band. This is inevitable when you are operating in the wireless spectrum. There are some very sophisticated techniques that can achieve very high bandwidth efficiency.